The traditional corporate perimeter has dissolved. Modern enterprise architectures are defined by deep external software supply chains and the rapid integration of autonomous AI systems. Static, descriptive governance checklists are too slow to counter threats that adapt in real time. Evaluating a vendor on an annual cycle or relying on manual code reviews leaves massive gaps when dealing with systems that write their own execution logic. Achieving actual operational resilience requires mapping global GRC standards directly into automated, enforceable technical boundaries. To achieve this, organizations must map their operations across a unified 4-layer defense stack. This blueprint maps the entire operational surface, from the external network edge all the way down to the runtime AI execution sandbox. Unifying static policy with dynamic infrastructure is the only method to secure both legacy hardware and autonomous AI within the exact same enterprise environment. The first layer isolates a physical and network edge. ISO 27002 Control 8.14 demands the elimination of single points of failure. System architects achieve this by deploying active-active software clustering and geographically dispersed cloud regions, ensuring system availability continues uninterrupted during localized disruptions. At the perimeter, Control 8.23 mandates strict web filtering. By relying on heuristic analysis and TLS decryption, the network gateway actively blocks employee access to compromised delivery sites and silent drive-by downloads. Securing the physical lifecycle of enterprise assets requires a different approach. Control 8.10 dictates the specific methods organizations must use for information deletion. Dormant APIs and orphaned virtual machines, often called ghost assets, are frequently ignored by security monitoring tools. Attackers actively seek out these forgotten endpoints to use as unmonitored staging grounds for lateral network movement. Before decommissioning these assets, administrators must enforce the 3-2-1 backup rule, maintaining 3 copies of data across 2 distinct media types, with 1 copy stored offsite. Once archived, verifiable data sanitization begins. In cloud-hosted environments, systems execute cryptographic erasure, destroying the decryption keys to render the underlying data completely unreadable. For retired physical media, compliance requires outright physical destruction. By strictly controlling hardware lifecycles and enforcing edge filtering, organizations eliminate the lowest hanging entry points used by automated threat actors. Below the network edge sits the second layer, proprietary and open-source software supply chains. Commercial off-the-shelf software operates directly inside the corporate network. Because it has access to local system resources, acquired software must be systematically audited before deployment. This includes direct binary analysis and validating SOC2 Type 2 reports to confirm the vendor's secure development lifecycle. These audits feed directly into the NIST Special Publication 800-161R1 framework, which forces enterprises to abandon generic vendor questionnaires in favor of quantifiable risk metrics. NIST establishes a 4-tier supplier categorization model based strictly on maximum tolerable downtime. A Tier 1 mission-critical supplier requires continuous real-time monitoring because its failure would halt enterprise operations within 24 hours. This diagram shows the modified Herfindahl-Hirschman Index, a mathematical formula adapted to calculate vendor concentration risk. Organizations input the percentage of operational dependency and the supplier's security rating to generate an exact quantitative risk score. When that HHI score exceeds 2,500, it signals severe concentration risk. To prevent systemic failure if that specific technology stack goes offline, the architecture must immediately branch out and diversify. External vendor risk is matched by the internal threat of source code manipulation, requiring rigid boundaries within the enterprise version control system. Developers must cryptographically sign every local repository commit using GPG, SSH, or SMIME keys. Administrators enforce this by enabling Vigilant mode branch protection rules. The version control system evaluates the cryptographic signature on every single push, automatically rejecting any commit that is unverified or spoofed. Cryptographic merge enforcement and quantitative HHI metrics mathematically prevent attackers from impersonating trusted developers or exploiting singular vendor failures. The third layer protects the convergence zone, where web APIs feed directly into machine learning ingestion pipelines. Modern web interfaces adhere to the OWASP API Top 10 framework. This mandates strict rate limiting to prevent resource consumption attacks, and server-side token-based checks to eliminate broken object-level authorization vulnerabilities. Once data passes the gateway, it enters the ML pipeline. Here, the system must defend against threats mapped in the OWASP machine learning top 10, specifically data poisoning in training sets and model poisoning, where internal weights are deliberately manipulated. The most critical pipeline threat to enterprise automation occurs precisely during data ingestion, indirect prompt injection. Large language models process system instructions and external data as unified natural language tokens. Because they do not structurally separate the two within their context window, the model executes hidden malicious data as if it were an authoritative system directive. Adversaries engineer payloads to remain invisible to human readers while remaining perfectly readable by the LLM. They do this by zero-sizing text or using CSS suppression tags to bury adversarial commands inside an otherwise normal web page. Malicious instructions are also frequently encapsulated within XML or SVG character data blocks inside image source code. The moment the model parses the page elements, it ingests the poison. Hardening the API gateway and systematically stripping hidden structural data prevents attackers from hijacking the system's operational goals before the external data ever reaches the AI agent. The final, deepest layer of the stack is the autonomous agent sandbox. Autonomous agents generate novel code at runtime based entirely on natural language. Because these execution paths are non-deterministic, static compile-time security controls no longer apply. This architectural layer operates on a core assumption: the agent will eventually ingest a compromised prompt. Therefore, the strategy shifts entirely to containing the blast radius of that compromise. Standard Linux containers share the host operating system's kernel, which leaves them vulnerable to kernel escape exploits by a hijacked agent. Agents require strict hardware-level isolation. Systems utilize lightweight micro-VMs or secure user space kernels, like gvisor, to intercept all system calls before they ever reach the host. With the execution environment isolated, the file system must be entirely locked down. This diagram outlines a secured directory tree. The root file system is mounted strictly as read-only. Any writable storage is limited to highly restricted, memory-backed temporary directories, which are capped in size and flagged with No-Exec to block the execution of binary payloads. Network access follows a default deny egress model. The architecture blocks all outbound connections, except those strictly required to reach authorized LLM providers. To seal off a critical cloud vulnerability, host-side IP tables must explicitly drop any container-originated traffic directed toward the Cloud Instance Metadata Service at the IP address 169.254.169.254. If an agent successfully accesses that endpoint, it can harvest the underlying host's IAM role credentials, allowing it to instantly compromise the broader cloud organization. Finally, static secrets are forbidden in the runtime container. Agents utilize an on-behalf-of architecture, querying a host-side proxy to request short-lived, single-use, just-in-time tokens that expire immediately upon task completion. Applying absolute containment across hardware, file systems, and identity neutralizes the impact of compromised code. The hijacked, non-deterministic agent remains trapped in a powerless state. Stacked together, these four layers form a fully operational, unified defense architecture. Securing the modern enterprise requires moving away from isolated compliance checklists and building an interdependent defense-in-depth framework. Governance standards like ISO 27002 and NIST supply chain controls establish the required operational baselines. Modern sandboxing primitives and cryptographic version control system rules translate those policies into automated enforcement. The GRC mandates dictate the organizational intent, while the technical primitives provide the hard, immutable boundaries. By strictly aligning global risk standards with concrete infrastructure rules, enterprises can definitively secure code provenance and safely contain the non-deterministic volatility of autonomous systems. For decades, enterprise networks operated on an assumption of relational trust. Security architectures focused heavily on establishing hardened external perimeters to protect soft, inherently trusted internal environments. Advanced persistent threat actors recognized this structural vulnerability and shifted their focus. Instead of battering the perimeter directly, they began targeting the software supply chain, hiding their malicious operations inside the very tools those internal environments already trusted. The historical precedent for this tactic traces back to this diagram illustrates the necessary architectural shift to counter such threats: algorithmic governance. This model demands that security architectures verify execution starting at the lowest layers, like the operating system kernel, and ascend to high levels of cryptographic verification. Under this structural imperative, trust is never assumed based on network location or past behavior. It must be continuously computed and mathematically validated at every step. The challenge for modern enterprises is implementing this rigorous verification across massively complex, distributed networks without introducing prohibitive friction that halts rapid deployment cycles. To resolve the tension between speed and security, DevSecOps frameworks have abandoned qualitative security promises. They require a transition to automated, artifact-driven cryptographic proof to ensure system integrity. Creating that cryptographic proof requires two primary disciplines. The first is active application security testing, integrated directly into the continuous development pipeline. On this continuous delivery timeline, SAST examines source code for flaws, while SCA scans third-party dependencies. After the build, IAST and DAST activate as black box simulations, attacking the running application to expose runtime vulnerabilities. The primary hurdle is tool sprawl. Systems generate massive, fragmented vulnerability datasets, cluttered with duplicate entries and endless false positives. The complexity increases in proprietary cloud runtimes. Generic security scanners often fail on specialized syntaxes, like Salesforce's Apex and Visualforce, requiring custom-tuned engines to prevent unauthorized permission escalations. Autonomous platforms introduce an entirely different edge case: AI agent prompt injection. In this scenario, attackers embed malicious natural language instructions within standard web forms or customer comments. When processed, these hidden instructions override the agent's core programming. The compromised agent acts on behalf of the attacker, executing unauthorized actions such as the exfiltration of sensitive CRM data using elevated administrative permissions. While pipeline automation establishes a baseline, protecting complex, high-risk code paths requires specialized semantic verification and human-centric threat modeling. The second verification discipline addresses the external codebase, requiring strict management of external repositories and third-party software risks. Recent policy directives forced a rapid maturation of supply chain security. Regulations like U.S. Executive Order 14306 fundamentally restructured the federal compliance model. Centralized attestation validation was abandoned. The modern federal model places the burden of proof directly on the software vendor, transforming self-attestation into a legally binding declaration that requires auditable technical evidence. Under the European Union's Cyber Resilience Act, manufacturers are legally obligated to retain mandatory technical documentation for at least 10 years. To meet these strict legal standards, the Software Bill of Materials, or SBOM, evolved from a passive licensing checklist into an active, machine-readable security asset. Under updated global standards from CISA and the EU, metadata fields like cryptographic hash and generation context shifted to mandatory requirements. Capturing this exact build lifecycle context creates a verifiable record, preventing threat actors from silently injecting malicious dependencies during compilation. To ingest code safely, organizations now rely on curated repositories like Google Cloud's Assured OSS, which provide pre-vetted, patched, and cryptographically signed packages. Modern compliance demands standardized, interoperable data formats such as SPDX or CycloneDX that supply exact cryptographic proof of software provenance. Generating machine-readable SBOMs solves the theoretical problem. The operational challenge is executing those frameworks daily, at scale, without human hesitation. This validation architecture relies on an operating covenant, a constitutional constraint enforced through technical architecture. Operating on the principle of speed under law, automated policy as code engines instantly block any deployment bypassing compliance or privacy rules. Furthermore, a strict zero-trust posture is physically hard-coded across all system-to-system communications. Network connections rely on mutual TLS, or MTLS. Both client and server authenticate each other using X509 certificates issued by a trusted authority. These certificates feature short validity periods ranging from just 7 to 30 days and undergo automatic rotation. This constant cycling eliminates the threat of attackers stealing long-lived API keys. A hard-coded remediation matrix schedules fixes based on CVSS severity scores, mandating a 7-day window for critical vulnerabilities. Violating these SLAs triggers automated enforcement, from temporary operational suspension to immediate disablement of the affected software. By removing subjective human interpretation, the operating covenant transforms high-level regulatory mandates into executing physical laws of a network. The modern global software supply chain operates at a scale and velocity that renders manual inspection completely futile. Consider the sudden public disclosure of a critical zero-day vulnerability hidden within a widely used open-source component. When the zero-day drops, mature systems automatically ingest a Vulnerability Exploitation Exchange, or VEX, document, or a Common Security Advisory Framework feed. Here, the system instantly cross-references incoming VEX data against its live SBOM inventory, identifying and isolating the vulnerable library. Security teams transition from searching for exposures over weeks to verifying their environment in a fraction of a second. This immediate, automated isolation allows the application to continue running safely while developers patch the specific component, significantly reducing rework and preventing the accumulation of technical debt. By integrating the active testing of NIST application security frameworks, the strict metadata requirements of modern SBOMs, and the automated enforcement of the operating covenant, organizations finally achieve computational trust. Digital infrastructure is secured not through promises, but through verifiable mathematical proof. Releasing software filled with structural bugs introduces an immediate, severe threat to an organization's entire security posture. Treating security as a compliance audit pasted onto the end of a build cycle guarantees failure. When defects are identified late in the process, remediation becomes complex and expensive. True software resilience requires treating security as a continuous, foundational property. It has to be integrated across both the tactical software development lifecycle, or SDLC, and the broader systemic system lifecycle. The SDLC deals specifically with the operational mechanics of code creation. It moves from initial planning and functional requirements definition through physical source code implementation, and finally into unit and acceptance testing. The system lifecycle encompasses those development phases, but extends much further. It includes the software's transition into production, active maintenance, performance monitoring, and eventual secure decommissioning or disposal. Protecting data and preventing emerging threats requires continuous management oversight across these specific boundaries. Security controls must be interwoven through every phase of both life cycles to maintain strict code integrity. Integrating systematic security checks begins with understanding the development methodology. The chosen model dictates the operational rhythm of how and when these controls are applied. In the traditional waterfall model, development progresses sequentially through distinct, isolated phases. Because one stage must finish before the next begins, identifying security defects happens late in the cycle, making fixes highly disruptive. Modern approaches correct this isolated design. The spiral model systematically analyzes risk in iterative cycles. Agile and rapid application development rely on continuous automated testing and lightweight guardrails to verify security without slowing down the rapid sprint-level release pace. To measure and elevate these secure development capabilities, engineering teams utilize software security maturity models. These frameworks establish a baseline for an organization's current practices. This matrix compares two leading maturity models. On the left, OWASP SAM 2.0 is a prescriptive framework, providing guidance across 5 business functions and 90 security activities. On the right, BSIM 14 is an empirical framework, providing benchmarks against real-world practices across 130 active enterprises. Selecting the correct maturity framework allows development teams to ensure their security investments and architectural guardrails match the precise operational rhythm and risk tolerance of their enterprise. Before physical coding begins, developers must define specific security constraints during the system design phase. These are classified as non-functional requirements, parameters that define system boundaries and operational limitations, rather than specific features for the end user. Development teams translate these requirements into abuse and misuse cases. By explicitly designing scenarios where the system is manipulated, engineers accurately model its susceptibility to exploitation. This profiling activity directly drives the threat modeling process. Microsoft's STRIDE model is frequently used here to logically categorize threats at the specific system component level. This equation shows the DREAD quantitative framework, paired with STRIDE to calculate risk levels. It evaluates 5 variables: damage, reproducibility, exploitability, affected users, and discoverability. Each is rated 1 to 10. The arithmetic mean computes the final risk score, prioritizing vulnerabilities requiring immediate remediation. While STRIDE and DREAD focus heavily on system components, the PASTA framework takes a holistic approach. PASTA uses a 7-stage risk-centric methodology to integrate technical vulnerabilities directly with the broader business context. Executing a structured threat modeling process ensures that engineering efforts and security spending are aligned precisely with the operational severity and the actual business value of the protected assets. In modern DevSecOps environments, source code management platforms and CI/CD pipelines represent highly sensitive components. Attackers target these pathways to execute compromises and exfiltrate secrets. Protecting this pipeline requires hardening the build servers and establishing strict branch protection policies on primary codebases. This is the first defense against the unauthorized introduction of code into production. Teams must disable auto-merge rules. Pull requests require multi-peer reviews, and bypass controls must be disabled. To further secure the source code management platform, cryptographically signed commits must be enforced. This guarantees developer identity and mathematically prevents source code tampering. Beyond the source repository, the build pipeline itself is vulnerable. Mitigation strategies must align with the specific architectural flaws outlined in the OWASP Top 10 CI/CD security risks. To prevent poisoned pipeline execution, where an attacker injects malicious commands into the build process, unreviewed code must run in isolated nodes, and write permissions must be heavily restricted. Dependency chain abuse is mitigated by routing all external package downloads through an internal proxy. Every artifact must undergo strict checksum verification before it enters the build server. Insufficient pipeline-based access controls are resolved by applying rigid least privilege constraints to the pipeline's operational identities and execution scopes. Hard-coded keys are strictly prohibited. Configuration files must be scanned for secrets, and credentials must be injected dynamically via secure vaults to ensure absolute credential hygiene. These controls are managed programmatically using policy as code engines. This enforces automated static application security testing, or SAST, and software composition analysis on every single build, without requiring manual intervention. Enforcing flow control, identity verification, and strict secret management is the only architectural defense capable of stopping catastrophic supply chain execution before it reaches production. Once the pipeline is secured, coding teams must strictly adhere to secure development baselines during the physical implementation of the source code. All inputs require rigorous server-side validation. Developers must use an allow-alest approach, verifying that incoming data exactly matches expected schemas, types, character ranges, and lengths before any processing occurs. Data returned to the client must be contextually encoded. Applying techniques like HTML entity encoding prevents malicious data from executing within the browser or other client-side interpreters. At the database tier, applications must enforce parameterized queries and stored procedures. This abstracts executable SQL logic completely away from raw user data, stopping SQL injection attacks. Error handling must be designed to fail closed. Error pages should return generic messages, blocking access by default to prevent the leakage of sensitive system details, session tokens, or debugging stack traces. Securing API communication is critical. This table compares REST and SOAP architectures. REST relies on standard HTTP transport, offering high performance and support for JSON and XML. Conversely, SOAP demands strict XML parsing and complex interface contracts, lowering performance but offering built-in fault structures. Systematic verification of these programmatic controls against standards like the OWASP Application Security Verification Standard, specifically Level 2, neutralizes the injection flaws and memory logic bypasses that threat actors rely upon. The threat surface extends beyond internally developed code. Commercial off-the-shelf software, open-source packages, and third-party SaaS integrations demand identical security scrutiny and verification. To manage this massive supply chain risk, organizations turn to the NIST Secure Software Development Framework, or SSDF. It serves as the mandatory standard for outcome-based supply chain risk management. The SSDF outlines 4 core pillars: prepare the organization, protect the software, produce well-secured software, and respond to vulnerabilities. The protect and produce pillars dictate mechanisms to secure source repositories and design secure architectures, verifying code release integrity at every step. Operationally, this requires the delivery of software bills of materials, or SBOMs. These structured inventories track every single third-party dependency utilized in the build. This tracking is combined with SLSA provenance attestations, supply chain levels for software artifacts. These attestations mathematically verify that the code's integrity has not been compromised from its origin through to deployment. The architecture of a secure SDLC requires rigid milestones: strict source code management flow control, automated pipeline integration, threat alignment with PASTA and DREAD, and strict ASVS coding baseline adherence. Security by design is an active, continuous engineering practice. By linking internal coding controls with external supply chain provenance, enterprises establish a fortified, resilient lifecycle capable of defending against modern software compromises.